All right, so today will be the first of a series of 2 talks in the Quiver Meeting. And the first talk today will be given by Michele Del Zotto and Marco Fazzi. And Michele will now tell us about heterotic strings on ALE spaces revival. Give the first segment. Take it away.
All right. So thank you very much, Julius, and to the group at Imperial for the invitation and the interest in our work. This is indeed a revival, a little bit of a revival of heterotic strings on ALE spaces, which we started in Uppsala with Muyang and Paul Constantin over the past year. And then also Marco joined the group at Uppsala. We started discussing, and so there is an injection, which is very on topic for this seminar. So this talk is going to be based on, oh my God, it doesn't go on like this. This talk is based on a long series of works. The first work is a work that I wrote about 8 years ago, together with Lakshya Bhardwaj, Jonathan Ekman, Tom Brudelius, David Morrison, and Kumrun, and where we embedded heterotic string into F-theory scenarios. Well, not just any little string, not just the heterotic ones. Then there was a work that I wrote in 2020 with Kantaro Mori, where we discussed the interplay of 2 groups and T-duality for little strings. And those then became ingredients for this series of papers together with Muyang and Paul, 2 of whom are published, and these are the archaic number. And then there is a third one which is upcoming, and hopefully it will appear before the end of the month. Similarly, there is another work together with Marco and with Suvendu that is going to appear, and a 7th work, which is in progress together with Andreas Braun, Muyang, and Paul. So today, what I will discuss is the certain aspects of the QFT side, if you wish, of the 2nd and the 3rd work, as well as the 5th and the 6th work. In my part of the seminar, I will discuss mostly this work 2, 3, and 5, and Marco will discuss parts of work 5 and work 6. And instead, in the following week, we will embed ourselves into geometry, and Muyang will introduce this geometrization of little strings and the tools developed in the first paper, while Paul will discuss the 2nd one and this work in progress with Andreas. And without further ado, I can now start. More or less, you have the structure of this series of talks is that one. Over the past decade, we've made lots of progress, both in understanding generalization of symmetries and the structure and classification of higher dimensional field theories. No? So over the past decade, a lot of work has been done about higher dimensional CFTs, 6D CFTs, 5D CFTs by many people in the audience, as well as about generalized symmetries and the structure. And in the project that we discuss this series of 2 seminars, we combine these two ideas to revisit the well-known beautiful story of T-duality of heterotic ALE instantons. No? So we learned some new aspects of this old problem. So let me remind you how does it work. We have the 2 heterotic string theories. They are T-dual one another, and they have gauge degrees of freedom, and therefore they have instantons. An instanton in 4 dimensions is a point, in 5 dimensions is a line, in 6 dimensions is a string. In 10 dimensions, an instanton is a 6-dimensional object, which is also known as the heterotic NS5 brane. And so these heterotic strings have heterotic NS5 branes. They are the instantons of the heterotic. There is an E88 version and a spin32 mod Z2 version. Their theories, the world volume theories, have been figured out back in the 90s. The one on the spin32 side is a Lagrangian theory, and so it essentially doesn't have any mystery. Well, it is a little string eventually, but it has a Lagrangian description. Instead, the one on the E8 times E8 side is much more exotic and interesting, and it was introduced and discussed in this nice work by Amihai and Ganor. Now, in order to match them across the T-duality, one recognizes that they share SO16 square subalgebra, and exploits that to track the two symmetries across the T-duality. And there was this remark, more or less in the same period, that one can decouple gravity from the heterotic string, and if one has from strings in general, not just from the heterotic, and if one has an S5 branes, one can do that in such a way that one is left out on the word volunteer on the S5, which is a theory that has T-duality, a Hagedorn density of states, and no gravity. No? So this theory is what was then called the little string theory. Of course, for this seminar, I don't think much more is needed as a reminder. But that's the theory that we're interested in today. Another thing which is interesting is that the little string theory is a theory that has a scale, an intrinsic scale, and that below such a scale, the dynamics is that of a six-dimensional superconformal field theory, and above, instead, one gets this extra mode, the little string, which is responsible for the T-duality of these models. Now, in this talk, we are interested about the T-duality of the LE instantons, which are essentially NS5 branes which probe LE singularities. Okay, so in this case, however, like the instantons are also labeled crucially by choices of flat connections at infinity, because these are spaces that have a non-trivial P1 on the link of the singularity, and therefore they on top of telling you what is the number of instantons that I have, I also need to tell you about a flat connection at infinity. And to characterize the latter, I have to prescribe a way of mapping the fundamental group of the link of the singularity into the gauge group of my theory. And in this case, this is given by mapping the group gamma, which is the subgroup of SU2, which is used to define the LE singularity, into the gauge group. So on the 88 side, I have two group morphism, two embeddings, if you wish, of gamma inside the 8, and on the spin 32 side, I have an embedding of gamma inside spin 32 mod Z2. Okay, so this is how we label the instantons. Now, yes.
Related to this, in case it's not part of those ADE, more than ADE. So let's say if you have a symmetric group embedding into a spin, do you know any work which did classification of embeddings?
If it is not simply laced.
If it's not one of the gammas that show up in ALE. So let's say symmetric N.
Say another subgroup of the gamma would be subgroups of SU2, finite subgroup of SU2. And you're asking if you have a subgroup of U2 or a different group altogether.
Just a discrete group embedding, even more. Oh, thank you. Yeah, but if you don't know, I don't want to confuse the
maybe we can discuss it later.
Just a comment for Ami. Maybe, but I'm not completely sure. You can have a look at this mathematician Darren Frey, who is also collaborating with Tom.
Yeah, I'm familiar with his work on dihedral groups. Work.
No, I just didn't remember whether he also treated some other finite groups in one of his single author papers, not the one with Tom. I'm not completely sure though, so I don't want to.
There's also some work by Lustig, possibly.
Yes, exactly. I remember the work by Lustig and some work also by Serre.
I see.
I'm not sure if this has been carried out completely. I mean, there are many choices. In what follows, there will be a question which is related to yours.
Okay.
But I will point it out when it comes.
Thank you. Yes.
But it's really Pandora's box. It's and you will see in which sense. So for now, the groups gammas are discrete subgroups of SU2. So they are labeled by an ADE series by the McKay correspondence. Now, on top of that, we have the number of heterotic n fibrils, and so we have these 6-dimensional little string theories, which are labeled by the number of n fibrils and these prescriptions of embeddings of gamma inside either E8 times E8 or spin 32 mod Z2. Of course, the T-duality from the heterotic string above induces a T-duality for all of these families of theories. How does it work? So on the right-hand side, as I said before, the theory is Lagrangian, and so one can exploit the Lagrangian to figure out what are the theories that you obtain by orbifold. No? And this was done in a beautiful series of papers by Kenny Triligator and Bloom in around 96, 97. No? All the cases on the right-hand side can be treated theoretically as orbifolds of the theory figured out by Witten, of this Lagrangian of the heterotic instanton by Witten. And on the left-hand side, instead, we have a full analysis of the cases in which the flavor symmetry group is maximal. So this is the case in which these embeddings are just the trivial group. No? And this was done by Aspinwall and Morrison exploiting F-theory techniques. However, then there are also many other papers that studied the more general instanton configuration where the embedding is not the one that leaves the only 8 unbroken, exploiting again F-theory and the duality between F-theory and heterotic. However, the question was still open when we were studying this. When we started studying this, there were many cases for which one would have to construct an appropriate geometry and try to figure it out. And the question was whether we could find a systematic understanding of this without having to exploit geometry of the time. And this is done thanks to this 6D conformal matter approach to 6-dimensional theories. And that's the first result, if you wish, of this collaboration, which is a very simple result. No, we just understood what are the various building blocks that need to be gauged together to construct these theories. I will just outline the results, and then this is something that I will discuss more in detail later in this seminar today. Then, as a second result, there was trying to establish criteria to match them with the known list. No? So, if we assume that these on the E88 side we have a way of building them, exploiting 6D conformal matter methods, then we want, for each theory that we construct, we want to find the corresponding T-dual on the side that we know since the 90s. So, for each of the theories that we begin with, we should have a T-dual, which is a theory that is known. No? And so, how do we match them? There is the criterion that the dimension of the Coulomb branches must match. But then, thanks to this work with Cantaro, now we have also the matching of the two group structure constants, which is a much more stringent criterion. And with that one, we could kind of identify T-dual pairs in all cases. There is a third criterion, which is the matching of the Higgs branches. And that is something that we started exploring together with Marco and Suvendra in this upcoming work. And it will be discussed in the structure of the Higgs branches of these theories will be something that Marco will discuss in his seminar. A third part is explicitly checking that the T-duality that we conjecture exploiting the matching of the two groups is effectively a T-duality that can be is compatible with this dictionary with F-theory. And in a sense, that's a proof of the conjectures, because we can literally reproduce the T-duality from geometry. And this is something that will be discussed in the talk by Mu Yang next week. And out of that, an application is that we can kind of bootstrap what is the geometric engineering limit of heterotic strings on LE spaces by removing the NS fibrils. And we find that in many cases this is related to this phenomenon of fractionalization of the N9 brane, or the fact that if you start from an LE space and you prescribe some non-trivial fractionation at infinity, there is a minimal instanton number which is trapped at the singularity, and exploiting our method, we can determine it for whatever choice of connection at infinity. And so there is also an application of this from the Higgs branches about the heterotic scalar manifold for this system that it follows from the results that Marco will discuss later. And then, as a further application, exploiting this dictionary with F-theory, we realized that there were many more examples of T-dualities than we naively expected. And for instance, we found that there are exality diagrams or manyality, I don't know, polyality diagrams in which all the vertices of this diagram encode, for instance, in this case, it's an exality. All these vertices encode a flavor symmetry for the little string theory, and we can construct a geometry for which all of these limits in heterotic little string theories are explicitly realized. So it's an interesting application which has a very deep interplay with the geometry of K3. And this is something that will be discussed next week in the seminar by Paul. We have many more examples than the one that I presented, and it's also in this upcoming work with Andreas Braun, who is the master of K3s. That's it for the overview of the results. And now I want to briefly outline these applications of generalization of symmetries to duality, which is the first ingredient that we use. Then I will move to the conformal matter method. So as far as generalization of symmetries, I think many of you have been exposed to talks on generalized symmetries, and so I will be very brief. What I want to say is just that they give interesting constraints on dynamics. The constraints on dynamics that we get are essentially generalization of what you can do with anomalies. You know, for example, that there is 2th anomaly matching. If you have a theory in the ultraviolet and a theory in the infrared, the anomaly have to match. Now, if you have generalized symmetry, instead of an anomaly TFT, you have a symmetry TFT. And again, the symmetry TFT, if the RG flow is symmetry preserving, must match across the RG flow. Similarly, if you have dualities between theories, you expect that the anomaly have to match. And again, if you have generalized symmetries, we have symmetry TFTs that must match. Okay? And so this type of application is interesting for us. And the matching of the two group structure constant is an example of this kind. In the paper with Cantaro, we discussed the matching in the context of little strings, and then Cantaro, Lee, and Tachikawa, shortly after, brought a paper in which they find a similar application of matching two group structure to constrain cyber dualities among 4D n equal to 1 theories. And this is an interesting application of this higher symmetry, generalized symmetries. So how does it work for little string? For little string, we focus on a continuum group symmetry. There are also discrete versions, but for today's talk, we just focus on the continuous part. That was essentially discovered by Cordova, Dumitrescu, and Intriligator, thanks to a generalization of the Green-Schwarz mechanism that I will discuss in a second. But the idea of a two-group is that you have a ordinary symmetry, a zero-form symmetry, in this case, the Poincaré symmetry, the R symmetry, and the global symmetry of your little string, which mixes with a one-form symmetry. And the one-form symmetry that is crucial for us is a special one-form symmetry that arises in the context of 6D little strings, which captures the little string charge. Like it's a one-form symmetry charge that counts the number of little strings in your theory. It measures the little string charge. And the amount, the intensity, if you wish, of the mixing of these various factors is captured by some constants, which are the two group structure constants, if you wish. Now, how can we think of them? We can think of them literally in terms of a Green-Schwarz mechanism, but to discuss it, I need a little bit more notation. So remember, like the dictionary between F-theory and six-dimensional theories, there is a geometry. In this geometry, there is an intersection pairing. The strings arise from D3-branes wrapping curves in the base of F-theory. What matters for us in this slide is the fact that there is this Dirac pairing, which is this form defined in the basis, which is a symmetric form. It's the Dirac pairing between BPS strings. In the case of 6D TFTs, this Dirac pairing is a positive definite. In the case of 6D little strings, the Dirac pairing is like an affinization of the Dirac pairing of a CFT, where the affine root is the little string charge. Okay, so the idea is that what does it mean that there is this little string charge? It means that there is essentially the hallmark of this one-form symmetry. It means that one of the tensors in the geometric engineering becomes a background. And this background is the background for this one form symmetry that we needed. No? Now, from this, we know that there is this zero eigenvalue that we can use to embed in the Green-Schwarz mechanism to extract the two group structure, exploiting stuff that was done in the context of gauged Higher groups by Baez, Satie, and Schreiber back in the 2000s, more or less. No, the idea is that you remember in 6 dimensions you have the Green-Schwarz mechanism of anomaly cancellation, which essentially says that you have to couple a certain specific characteristic classes to the tensor fields in order to cancel the anomaly. And if one of the tensor fields is this background for the little strings, we see that we can essentially mix the factors of global symmetry with the curvature associated to this to form background field. So the relationship between the two, out of which you can compute this two group structure coefficient, is essentially the fact that you have two ways of computing this flux. There is one version, which is the flux associated to the little string charge, is just the linear combination with coefficients given by the little string charge of the various curvatures associated to the form anti-self-dual tensor fields. And there is the intrinsic definition which gives the intrinsic definition of these two group structure constants. This is the work by Cordova, Trivigator, and Dumitrescu, which says that the mixing of the two group structure is associated to this identity. But then there is the Green-Schwarz mechanism, which says that these curvatures for the various tensors in the tensor branch are related to the same characteristic classes by a different equation, which is the equation below. And so if I plug the equation below in the first of the equations above, I have a way of reading off the coefficient for their symmetry, the coefficient for the mixing of the Poincare symmetry, and the various coefficients for the mixings of the flavor symmetry, just out of the data of the little string charge and the usual anomaly polynomial of the 60 theories. And as a result, we obtain this very simple formula for the two group structure constants. They are given in terms of this intersection pairing in the F-theory base, which is just the little string Dirac pairing, the entries of this imaginary root that corresponds to the little string charge, and some gauge theoretic data associated to the various vector multiplets along the tensor branch. And out of this, you see that the most interesting one and most constraining one is the one associated to the R symmetry. Because in the R symmetry, you see that you have the various dual Coxeter number associated to the various gauge groups along that arise in the 6D tensor branch that combine with this little string charge tensor, and therefore the matching of this KR across T-duality is a very non-trivial consistency check, because there are many data that incur in defining this two group structure parameter, the little string charge as well as the gauge group that arise during on the tensor branch. No? Now let's give some example of this formula. I hope that I have it. Yes. So you see, this is an example of little strings of type A. The base of the F theory in this case would be an affine diagram, no? And it has a K. It's called an IK codiagram singularity. You hear more about geometry next week, but the idea is it's just an affine diagram. No, it's an A type affine with a K of AK type. So it has K+1 nodes. And on top of it, you see these -2 are the labels for the self-Dirac pairing of the various strings in the tensor branch. And on top of it, we have these IN singularities. The IN singularities parameterize SUN gauge groups. So this is a code or a generalized quiver that says that I have a little string which has an AK type tensor branch, which is decorated by SUN gauge symmetries. At each of these intersections, there is a bifundamental for SUN. The T-duality in this case is just obtained by swapping the role of the base and the fiber. And so you have, on the other side, you have an SUK gauge symmetry and an AN type base for the quiver. And if you do the computation, you remember, you see, like in this case, KR, like the little string charge in this example is just 1 over all the nodes, because that's the affine root of AN type, no? And all the gauge groups share the same dual Coxeter, which is for SUN, it is N. And so you see, on one side, if I do this computation, I have to sum with multiplicity 1 k copies of the dual Coxeter of SUN, and so I obtain n times k. And on the dual side, it's the same, but with the roles swapped. So I have the dual Coxeter is k, and I have to sum n times to obtain that. And so I have the KR, in this case, is n times k, and they match across the T-duality. And the KP, you see from the formula, KP is proportional to the self-Dirac pairing minus 2 times this little string charge. In this case, the self-Dirac pairing is 2 for all of them, so this is 0. And this is a fact of life that KP can only be either 0 or 2. Because we demonstrated explicitly with Cantaro that KP doesn't depend on the blow up in geometry, and so theories that are whose tensor branches are associated by just the process of blow ups, they have the same KP, the same two-group structure constants for the Poincaré group, and so you can see that if you look at the possible LST bases, there are essentially only bases that are affine or blow-ups of affine diagrams, and they all have minus 2s as self-Dirac pairings, and so those will give KP equal to 0. Or there are the ones that are associated to blow-ups of the little string base of the heterotic string, and that one is the one that gives 2. And remarkably, this is exactly the number of M9 branes in the background. So KP, the two-group structure constant of the Poincaré symmetry, the mixing of the Poincaré symmetry with the one-form symmetry of the little string, is associated to the number of M9 branes. For all the ADE type little strings that 2,0 that arise from 2,0 or Higgsable down to 2,0, they have KP which is equal to 0. The one instead that comes from the heterotic, they have KP equal to 2. An open question, which is very interesting and on which I think Paul is thinking about and working actively on, is to construct example where KP is 1, which would correspond to, say, little string versions of the CH string, for instance. It's just a side remark, but for the moment, the one that we know how to construct have KP are either 0 or 2. And so for all the heterotic examples that we'll consider in the rest of this talk, KP will be 2, and I won't write it down. Okay, the most constraining one is KR, as I say. So now let's go to the heterotic, and I will finish soon, Marco. No. So let's go to the heterotic. We have the Hojava-Witten description. There are the two M9 nodes, the M5s, and now we probe it with a C2 mod gamma singularity, which means that we have to decorate the two M9s with this embedding of a discrete group inside of E8. And now, what are the building blocks? Well, the block that goes from 1M9 to 1M5 is one of these Orbi instanton theories, in fact, the minimal one that can be constructed. And all of them has been classified in this nice paper by Rudelius and Frey of 2017. You name it and you find it there. The piece in the middle is the conformal matter, 6D conformal matter of G-type, because it's just the theory supported between two M5 branes on an AE singularity. And the last part is another Orbi instant from one M5 to the other M9. And how do we put them together? These are all 6D, well-known 6D building blocks. And how do we put them together? Well, it's just a gauge. No? So we have a generalized quiver description for the little strings of E8 type. It's just obtained by gauging or fusing, if you wish, the Orbi instanton with the conformal matter and in such a way that you obtain a little string. So this is again fully classified Orbi instanton, conformal motion, and this fusion, which is the operation that generalizes gauging in 6 dimensions. No? You cannot just gauge in 6 dimensions, you always need to compensate it with an appropriate tensor multiplet that forms a tensor vector system to cancel the anomaly by a Green-Schwarz mechanism. And this is the mechanism called fusion by Alessandro, I think Tom and Jonathan. We called it gauging together with Guglielmo back in the day. So we fuse them and we get this generalized quiver. As an example, this is an example that I won't have time to discuss, but you will see many more in Marco's talk. But this is an example in which you can see that I'm trying to build a theory that has SO16 times SO16. I have an SO16 on one side. This is the Orbi instanton, in this case, just the one with SPP. And then there is the conformal matter, which is just a bifundamental in this case. And we have as many bifundamental as we need, coupled together by SU2P symmetry. K is equal to 2P in this example. And the theory that we obtain is this one. It has Kp equal to 2 because it's an heterotic theory, and Kr is 2m times P. Now, this one has an embedding in type 1 prime, which is very nice. You know that the M9 type 1 prime are mapped to O8 minus with 8D8 branes. And from these works by Amihai and Alberto and Brunner and Karch, we know exactly how to read off the theories at hand. And we know also that the T-duality is obtained just by swapping the role of the D6s and the NS5s in these diagrams. So like the heterotic side, the NS5 is the number of instantons and the D6 captures the singularity. On the spin 32 side, the NS5s captures the singularity and the D6s captures the number of instantons. So again, we have a case in which we swap the base and the fiber in F theory. You can check that also in this case, the KR matches, and the matching is kind of non-trivial. The way in which 2 times NP is obtained in the two cases is different, no? But still, it works. So are there more complicated examples? Of course, no? We know that type 1 prime is good for VK groups and D-type groups, but for the E6, E7, and E8, we need F theory. The geometric side of this will be discussed next week, but let me give you an example exploiting this field theory approach, where we do the fusion. So for instance, here on the left-hand side, I have one of these Orbi instanton theory for a singularity of type E6, and in which I'm saving a subgroup of E8, which is E6. So this side here, from 131 up to the first piece here, this is the Orbi instanton theory on the left. And I want, on the other side, I want, say, another subgroup of E8, say E7. And so I have the other Orbi instanton theory that I'm doing on the other side here. And then in the middle, I put the E6, E6 conformal matter, which is the 61316 series as a tensor branch. So this is the resulting theory. Does it have from the Mojave picture? This is associated with this fractionalization of M9 branes and M5 branes. No? We know that the M5 on an E6 singularity splits into 4 fractional M5 branes, which are parameterizing these tensor branches. And the fractionalization of the M9 is much more tricky, but it is determined again by the first slide of the Orbi on the Orbi instanton side. So these things behave as if they are exotic fibrates in element theory, and they are the M9 fraction, these minimal instantons which are trapped on the M9 brane from the presence of the singularity. What is the T-dual? From geometry, we can, and from matching the two group structural constants, we see that this is a theory that Trilighter and Bloom would have associated to an E6 singularity with this flavor symmetry that can be matched with the flavor symmetry that we have on the other side, with these structure groups that matches the one that we would compute from one side to the other. And now, again, in a very non-trivial way, you see the matching of this 69 plus 24n on one side and on the other is absolutely non-trivial. And so this is a consistency check that the model that we proposed really existed. Now, many more examples, many generalizations. We'll hear about them next week. One last remark: we can bootstrap this geometric engineering limit by just removing the NS5s. No, we remove the NS5. What do? we fuse together the Orbi instanton theory, one over the other, in such a way that we are left with a single G-gamma group. So in the example that we had before, we have to remove all this part in the limit in which we send the number of M5 branes to 0. We are left with a single E6 gauge symmetry, and the fusion is telling us how to glue this thing together. And notice that from the T-dual side, no, we had this T-dual theory. In the T-dual theory, you see, if I set n to 0, I'm not left without a theory. No, also on the spin 32 side, there is a knowledge of this minimal instanton number trapped at the singularity if I have a non-trivial flux connection at infinity. So this also is interesting because we also have the T-duals, which determines this geometric engineering limit on the spin 32 side. So all this can be verified exploiting geometry. And it's an interesting exercise from which we have learned many more T-duality exist. And for this, I refer you to the talk next week. Pandora's box that I was mentioning as far as Amihai's question is how about now geometric engineering heterotic on C3 mod gamma? Why not? No, it would be we would get theories 4-dimensional now, parameterized by embeddings of discrete subgroups of SU3 inside the 8 times C8 and inside of spin 32 mod Z2. They will be little strings in 4D related by T-duality. No, because we start, the mechanism is going to be very similar. No, and so like this is literally Pandora's box because like now the set of discrete subgroup SU3 is much more wild, no, and their embeddings inside the gauge group of heterotic strings also like hasn't been studied that much as for the discrete subgroups of SU2. So Pandora's box. And second remark, how about the Higgs branches? No. And that's something for which I pass the ball to Marco, and where we will hear about the ZN cases. And I thank you for your attention, and I apologize for going a little bit over time. Okay, so now I think I can pass the ball.
Let's give a quick thanks to Michele for this first part. That was very nice. Would you prefer that we ask you some questions now, or should we do an at the end discussion?
Maybe we can do it at the end discussions.
Okay, that's good for me. Yeah, let's continue with Marco. We'll definitely want to talk about the Higgs branch. So
of course,
let's have it.
Okay, I should be able to see my presentation slideshow. Okay.
Yep, this looks good.
All right.
There is a cursor. Okay, so
yeah, there's a cursor.
Marco Fazzi. Tell us about 3D magnetic quivers or 60 little string theories. In a moment.
Okay, sorry.
Okay, take it away.
So let me echo Michele in thanking Julius and Ami for hosting me here for the second time. So as the title says, I'm going to essentially take the ball from Michele's hands and construct the 3D magnetic quivers for the 60 LSTs that he just introduced. And that's going to help us identify what's the Higgs branch of these LSTs. So this is based on work to appear with Michele and Suvendu, but also some observations at the very end are going to be based on 2 papers that are already published with Suvendu, Simone, and maybe some observations also are going to appear in a work in progress with Paul Levi, who's a mathematician out of Lancaster. So the idea is very simple. We want to construct the 3D magnetic quivers for the 60 LSTs. Which LSTs? Well, only for the moment at least, the ones that are sometimes called E prime. So E little LST stands for the one coming from the NS5s of the 88 heterotic string, and the prime stands to indicate that we're actually putting the heterotic string on an orbifold. And as Michele said, essentially, given that I'm going to use always the type 1 prime construction, I'm restricted to either ZK or DK orbifolds. And for this talk, I'm only going to focus on type A. So the picture that you see on the left is what Michele just drew. We have 2 M9 walls at the end of the interval in a Rojava-Witten setup in M theory, the interval being the Z2 orbifold of NS1, and we can sprinkle a number of M5 branes in the middle. And importantly, we have to specify a flat connection at infinity for each of the 2 walls that essentially is a representation of the ZK orbifold group in the E8 gauge group provided by the M9 wall for each of the 2. Equivalently, I can reduce to type 2A, obtaining a number of D8 branes D6 branes and NS5 branes on the circle. So you see each M9 wall goes down to 108 minus plus 8 D8s, and the 8 D8s can be put essentially at will along the circle. Then we have a number of NS5 branes, essentially just as many as we had M5 branes, and then we have D6 branes placed along the circle. I will simplify a little bit this picture in this way. So dashed vertical lines are the 08s, vertical lines, solid ones are the D8s, horizontal ones are D6s, and the circles are the NS5s. And of course, for those of you who know about magnetic quivers, which is essentially all of the audience, you will have already recognized that I'm using the magnetic phase. So I'm already lifting the NS5s off of the D6s. And that's what I'm going to use to construct the magnetic quivers. So what's the motivation for doing this? The motivation is essentially settling an old question in heterotic strings. And what's the question? The question is, what is the hypermultiplied moduli space of the heterotic string on an ALE space, which is locally modeled by C2 mod ZK. So I'm already decompactifying, if you want, the K3 on which I have compactified the heterotic string. I'm taking the limit where the volume is infinity. I'm decoupling gravity, and I'm focusing only in the vicinity of the singularity. So first of all, a few facts that Witten proved. This space would be quaternionic Hiter. So this hypermultiple moduli space would be quaternionic Hiter if we were to consider also gravity in the game, which just means that the holonomy is actually contained in this group here, USP2, USPn. If the quaternionic dimension of this space is, say, n, it's known to receive both alpha prime and worksheet instanton corrections. But now, yes.
It's 2n.
Sorry, yes, it's 2n, SPN, yeah, or USP2n, correct. So now let's decouple gravity. So zoom in on the singularity. This thing becomes hypercalar. So the holonomy is just containing USP2n, as Ami just noticed. Importantly, it's Ricci flat, and the unique metric on this space should be the Ricci flat one. Perhaps even more importantly, most corrections disappear because these are very hard to compute, but the remaining ones, at least in the example computed by Witten, remain. The remaining ones make it into a smooth space. So what's the result by Witten? So first of all, he focused on a slightly simpler situation. He basically considered no instantons for the heterotic gauge bundle, so that we can take actually the curvature to be identically zero. And the full gauge group, if you want, from the two M9s is entirely preserved. So we don't care about that for the moment. So Witten showed that in the simplest case of k equals 2, so C2 mod Z2, a simple, or maybe not so simple, heterotic CFT calculation essentially produces for you the so-called Atiyah-Hitchin manifold, which is the, in some sense, simplest hypercalar space. It has quaternionic dimension 1, and it's smooth. So the classical supergravity calculation would show that the moduli space of the heterotic string on C2 mod Z2 is just R3 times S1 mod Z2, but then this gets smoothed out by the corrections that I talked about into some twisted bundle of S1 over R3 minus the origin mod Z2, which is the Atiyah-Hitchin manifold. Actually, before that, Sen, he did a similar calculation by using the dynamics of KK monopoles in the heterotic string. And in that case, as you can imagine, the R3 times S1 mod Z2 space gets generalized into a symmetric product of K minus 1 copies of R3 times S1. So a multi-tab knot space that can develop singularities if the monopoles touch each other. And corrections are expected to smooth out this space again. And there's a very nice proof by Ami and Alberto. They use the type on prime dual setup, if you want, the one that I showed, that I sketched before, that essentially, because of the monopoles can be identified with NS5 branes, which are stuck on the OA plane, this space should actually be smooth, not just for these, simple, in some sense, monopoles, but also SC2 monopoles, but also as we generalize to the full list of EN groups. So let's try to build our connection to 3D, which is the main topic, if you want, of the talk. So for k equals 2, it's also known that the Atiyah-Hitchin manifold is also the moduli space of 2 BPS monopoles of SC2, and that's also the Coulomb branch of 3D n equals 4, pure SC2. Okay, but then Ami generalized this, and for k greater than 2, we know that the moduli space of k monopoles of SC2 is also the Coulomb branch of pure now SUK, not SC2. So it's natural to expect that what essentially Sen did, the observation that Sen put forward, is that the hypermultiplet moduli space computed by Sen, so the smoothing out of that k-1 copies of R3 times S1 mod Z2, should be the space of BPS monopoles, k of them, of SU2, and that should be identified with this Coulomb branch of pure SUK, which I will indicate with this abbreviation. But then, even without knowing this, Witten put forward this conjecture, and he said, well, if the k equals 2 k's of C2 mod zk is true, then it must be true that essentially the hypermultiplet moduli space of the heterotic string on C2 mod gamma g, so any gamma of AD type, should be the Coulomb branch of 3D pure G. So that's a conjecture. And here we want to ask whether we can verify that essentially, at least in the ZK case, with the caveat that Michele already put forward, that we have many non-trivial choices. Remember that we have a choice of mu1 and mu2, and that's going to break the two gauge groups on the M9 walls into subgroups. Okay, this was not considered at the time. It was considered in the paper by Ami and Alberto.
I should say that since '99, I didn't hear of this point.
That's good.
That's impressive. That,
I'm happy that I deburied it then. So, in fact, the conjecture was verified. Okay, basically soon after Witten put out the paper, 3 different papers, Rosali, Peter Meyer, and Aspewell and Plesser, verified the conjecture in 3 different ways, using dualities with F theory, as Michele introduced, or briefly touched upon, using M theory directly, using 3D directly. And the nice addition, the nice bonus that we get from these papers is that you do not need to restrict your attention to the case of no heterotic, or if you want, trivial heterotic gauge bundle. You can also assume that you have a non-trivial gauge bundle. So the connection is non-trivial, but it will be flat at infinity, at the spatial infinity. In other words, we can add the instantons, so the heterotic NS5 brains probing the C2 mod ZK singularity that Michele was talking about, and we have to remember that F equals 0 is only valid at the singularity. So we at the spatial infinity. So we ask, what's the counterpart of this in 3D? And these 3 papers essentially showed, or proposed, if you want, gave evidence for this, that pure SUK gets swapped with SUK with M hypers, where M is the number of the heterotic NS5s that you added to the game. Okay, so that will be the prescription. And notice that this K with M hypers theory is good in the sense of Guyot and Witten, whenever M is larger or equal to twice the number of colors, which you can also derive in a Hanani-Witten setup via essentially the S rule. And this was noticed back then by Ami and Witten also. Okay, so we understand the prescription. SUK, pure SUK, should be swapped with SUK with a certain number of hypers, that number being equal to the number of heterotic NS5s that I add to the game. Why is that true? So let's go back to the type 1 prime engineering. Consider E88 heterotic string on C2 mod ZK in geometric engineering. So type 1 prime setup, dashed lines O8s, vertical lines D8s, horizontal lines D6s, and the dots are NS5s. As you can see, I picked a very specific type of prime setup, which is the one which is valid, if you want, for the choice mu1 equals mu2 equals trivial flat connection at infinity. Or for those of you who know this language, Katz label 1 to the k. Okay. Now, if I do that, and I remembering that I have, again, many non-trivial choices in principle of flat connection at infinity, but I do stick with the trivial choice on both M9 walls, I get this 60 electric quiver in 60. In 60, I get this electric quiver, which I think was also briefly introduced by Michele. So we have the 2 ramps, as you can see, and we have a plateau of SUKs. Now, the plateau of SUKs will be the conformal matter, even though here there's no conformal matter because it's just by fundamentals because we're doing the ZK. But more or less speaking, we have ramp plus plateau, and then plateau and down ramp. And this, if I cut in half the plateau, I can easily recognize 2 orb instantons, which are being fused or gauged together by gauging a diagonal SUK subgroup. And now, of course, the 08 plus 78 modulo certain caveat would be responsible for the D8 group. The lonely D8 that you see here in the middle of the quiver, essentially at the beginning, at the onset of the plateau, corresponds to the one flavor of this SUK algebra. But now what I can do is I can take 3 T-dualities in the brain setup, or if you want, I can take the T3 compactification of the theory and obtain a 3D quiver, which is that one, that was already pointed out. This factor was already pointed out again by Ami and Alberto, but also in the paper by Aspinall and Plester, and also in a paper by Intriligator. And why is this relevant? Well, because if you know a little bit of 3D, you will also notice that this is nothing but the mirror dual to what essentially Witten put forward, or again, Meyer, Rosali, and Aspinall and Plester noticed that. So the statement would be that the theory SUK plus M hypers that was proposed in those papers is nothing but the mirror dual to the T3 compactification of the 60 quiver that engineers, at least the low energies, DLST. So this in some sense explains the conjecture by Witten, at least for SUK. So if this whole construction is true, it's also clear that the heterotic hypermultiplet modular space in presence of M small e8 instantons on the ALE space, which is the same by definition as the Higgs branch of the E prime LST, should also be the same as the Coulomb branch of that nice quiver, one gauge node quiver. So K plus M hypers. And the dimension is very easy to compute. I don't need to, bore you with how to write down this formula, but you all know how to do that. But essentially, it turns out that the dimension of the space, Higgs branch or Coulomb branch, is K-1 plus M. And as Intriligator already pointed out in the 90s, the K-1 part can be understood as the number of Hiter moduli, so the blow-up modes of the C2 mod ZK orbifold, and the M can be identified with the locations of M identical instantons roaming around the ALE space. And of course, if you just plug K equals 2 and M equals 0, in this formula, you would get dimension equals to 1, which is correctly the dimension of the Hitchin manifold that Witten identified as the correct moduli space with no instantons.
So, so if you look at the quivers on top, so if you look at, I suppose that by K and M you denote UK.
Yeah, sorry, KU. Yeah, it's a U group.
Yeah, and but since you compute the dimension of the Higgs branch to be K-1 plus M, I suppose that the flavor M on top should all be made to a bouquet.
In a bouquet, yes, that's also correct. So these details are going to appear in the paper. I just didn't want to be
okay.
that precise if you want here, but correct. You should reinterpret that M box as a bouquet of M ones.
Okay.
You can do that too. Yeah, correct. Sorry.
Okay.
Okay, so as I stressed multiple times by now, this is just one example. This is the trivial flat connections at infinity for both M anomalous. But however, as I said, we have, whenever you say the word instanton, you both have the choice of instanton number and the connection at infinity, because this pi one is non-empty. Okay, so the obvious question is, what about the cases with non-trivial flat connections? So what if I start breaking the E8 flavor from each of the two walls? What is the correct 3D description? And the answer is magnetic quivers for the E prime LSTs. How do I do that? It's very easy. Let me again take the foundational paper, at least in this topic, by Ami, Santiago, and Marcus. Let me focus on the Kuiper prime setup. Let me move to the magnetic phase. So I lift all of the NS5s off of the D6s. And moreover, I also remember that this thing here is nothing but a fusion, if you want, of two orb instantons. So I just cut the type 1 prime setup in the middle. I obtain two type 2A setups, each of them with 88 branes. And I have a flavor SUK at the end of the tail. I can also bring in from infinity. If you want, I can reshuffle or reinterpret the semi-infinite K D6 branes as K D6 branes ending each on a separate D8 brane, which would be the picture here, top right and top left. And this just tells me how to read off the magnetic quivers for each of the two orb instanton constituents. So this is one known. Again, I take it from Ami's paper. I have a tail from 1 to K, which is, in other words, something called TSUK in the language of Guyot and Witten. Plus, I have a bunch of ones on top of the K. And I call that their number big M. I think this is what Michele called big N, but never mind. Essentially, I have N NS5s in the plateau, and I have K of them in the ramp, at least for this specific example. However, we know that for more general Katz labels, or if you want embeddings of ZKA into E8 or representations. The magnetic quiver is slightly more general. In fact, it's going to be given by a star-shaped quiver of one TSUK tail, one affine E8 dinking shaped tail. Remember, these are all U groups, plus a bouquet of ones over the K node. Now, the explicit values of these ranks Ri and Ri prime actually depend on the choice of mu left and mu right. You cannot pick them. They're dictated upon you by the choice of Katz label. And what is important here is that this number n is a number of full instantons. So if you want in F theory, the number of curves in the plateau of the orb instanton, and this is an arbitrary number. That's why Michele said in the geometric engineering limit, you can take this number to be 0. You just remove all of the M5s in between the M9s. However, this number here, n mu, is not arbitrary. This you cannot pick. This is dictated again upon you by the choice of Katz label. And it has to do with this fractionalization of the M9, or if you want in F theory, it has to do with the number, it's the same as the number of curves in the ramp of the orb instanton, or in type 1 prime with the number of NS5s before essentially the ranks stabilize. Okay. But from the type 1 prime perspective, these are just NS5 rings, both of these guys. There is no difference. And this was actually pointed out in a, I think, little known paper by Ami and Alberto called Monopoles in String Theory, which is a very nice paper, in a slightly different language. Then it was reinterpreted in the 6D conformal matter paper in more general terms. And now what I have to do, it's obvious, right? I just take the two magnetic quivers for the two orb instantons and I glue them. And how do I glue them? Well, I have to glue them along the K node, essentially because if we go back to the type 1 prime setup, at least in this very simple example, I lift everything off. This part here, which will be responsible for the tail 1, 2, and so on up to K-1, disappears. It's not there anymore because I have two endings, left and right, dictated by the choice of label. So it's obvious that the magnetic quiver at finite coupling for all gauge algebras is this one here, where I have, again, a bouquet of ones, now M left plus M right. And remember that each number M is composed of an arbitrary number, N, which I can take to be 0, as Michele did, plus a number which I cannot decide. It's N mu, and it's dictated by the Katz label. So now, good, we have constructed the finite coupling magnetic quiver, but we know that magnetic quivers are nice because they can probe the infinite coupling, what Ami likes to call infinite coupling Higgs branch, at least for the orb instantons. So what do we do in the little string? Well, I think it's obvious what we do. We just perform M left plus M right, small E8 instanton transitions. Namely, we turn the bouquet of ones, which was here, into M left copies of the affine E8 dinking, mirrored, if you want, along the vertical axis on the left, plus M right copies of the affine E8 dinking, the usual one, on the right, plus the ranks, again, dictated by the choice of Katz labels, if they were there. For example, for the 1K, 1K choice of labels, all of these ranks are just 0. So you will be left with K and then a certain number of copies of E8 affine on the left and on the right. Just one remark, which is important for LSTs, but not for orb instantons. I can call this, if I want, magnetic quiver at infinite coupling. However, this is not the Higgs branch of the LST at infinite coupling. That does not mean anything. The LST is a quasi-local QFT, which has a UD cutoff. It's a mass scale called that M string. And above that, I need to complete it probably with string theory. The UD completion will be string theory itself. Below it, it's a QFT, which is local. And it has the description that we gave before, so the 60 electric quiver. So when I say infinite coupling magnetic quiver or infinite coupling Higgs branch for the LST, we actually mean that there is at least one tensor which is non-dynamical. So its size, if you want, the scalar in that tensor is fixed. And that sets the scale of the LST, which I think sometimes in this paper was called, and even in the older paper was called MS M string. Okay, that's just a caveat. Okay, now if this is true, I can easily compute the dimension of this object. Let me insist in calling it Coulomb branch at infinite coupling. And the dimension of the quaternionic dimension of the heterotic hypermultiplet moduli space in presence of M E8 instantons on the C2 Mazikei LE space is given by the dimension of this Higgs Coulomb branch here, which you can easily compute, and it's going to be given by this. Okay, so you see again the 30, which is typical typically arises from the E8 instanton transitions. You see the k-1 because of the number of blow-up modes, but also you see that we have some new numbers, if you want, a new presence because of the Katz labels. Let me stress again that in the easiest 1K Katz label situation, so trivial flat connection, both left and right, all of these ranks are 0, so you would not see this point. So how many minutes do we have, Julius? 5-ish?
How many minutes do you want?
5 is enough. I don't want to bore
Let's do
you.
5.
Okay, so tests and conjectures, because I like to add some conjectures to the Quiver meetings. Okay, so by definition, the dimension of the Higgs branch at infinite coupling, or by that I mean what I just said in the previous slide, of the LST specified by mu left and mu right, will be equal to the dimension of the heterotic hypermultiple moduli space with them E8 instantons on the ALE space. So let's check the dimensions match. So this thing here, the dimension of this Coulomb branch, should be equal to multiple objects if you want. First of all, it should be equal to the dimension of the infinite coupling Higgs branches of the two orb instanton constituents minus the SUK that we're gauging. Because remember that the Higgs branch by definition, the dimension of the Higgs branch by definition is given by the total number of hypermultiplets. And by that, I also include the tensor multiplets that have transitions into hypermultiplets minus the total number of vector multiplets. So we're gauging the SUK, flavor of the two orb instanton together. So I should remove that. And then, of course, this quantity here nicely matches with that one. Moreover, an independent match, even though this is only valid for the 1K situation. So trivial flat connection at infinity for both M9 walls. And Sriligator pointed out that essentially cancellation of gravitational anomalies forces something. So it forces that the Higgs branch dimension of this thing here, of the LST, should be equal to 30 times the total number of instantons plus R, which is, as I said, the number of, sorry, I didn't say that, which is the number of blow-up modes of the orbifold. And that, in this specific case, is equal to 30n plus 61k-1. That matches with this dimension too. And finally, perhaps more interestingly, or not, I don't know, Noppadol, Cantaro, Yuji, and Gabi, in a very nice paper, in which they were trying to construct moduli spaces for E8 instantons on ALE spaces, also constructed as a bonus the class S compactification of the orb instantons. That turns out to be a fixture, so a sphere with 3 punctures, called that Y1, Y2, Y3. And you can easily compute the dimension of the Higgs branch of that object via formulae that were given by Ciacaltana, Wissler, and Yuji. And again, you sum the dimensions of the two of the Higgs branches of the two fixtures, remove the dimension of the SUK that you're gauging, and you obtain the same number. Also, the symmetries on the Coulomb branch, at least the visible ones, match from the expected breaking of the two E8s from the LST. So that's also another match. Conjectures. So these are fixtures, sphere with 3 punctures. They turn out to be regular punctures. And the punctures, as you know, are 1-to-1 with partitions of, a number which is the rank of the algebra that defines for you the type of the class S theory. And it turns out that the puncture, let's call that Y1, both for the left and right orb instanton, contains a part which is 1 to the K. As Noppadol and friends explained, this 1 to the K is essentially responsible for the SUK flavor symmetry of the orb instantons. So the picture that we would like to propose is the following. If these are the two fixtures associated with the two orb instanton constituents of the LST, there should be an operation, so a gauging of the 1K subpart of the two punctures Y1 on left and right via an SUK tube that produces a new class S theory called that SM prime with 4 punctures, 1, 2, 3, 4. And maybe that could be done with this OP of punctures technique, which is detailed in this paper. And then it's natural to expect that, again, the Coulomb branch dimension matches with the Higgs branch dimension of this new class S theory. If you want to be really fancy, the two fixtures, because we're gauging a diagonal SUK, the Higgs branches, the Higgs branch of the new guy should be obtained by essentially a hyperkähler quotient, or if you want to, again, as I said, be very fancy, holomorphic symplectic quotient of the Higgs branches of the two fixtures. So another conjecture, or if you want one that follows straight from the previous slide, because we know that the compactification plus mirror of class S theories, Michele's laughing, with or at least fixtures with 3 punctures should be a Sicilian theory. this has 4 punctures, so it should be a Sicilian plus. So, you know, the guy with 3 legs plus a tail, if you want. And this should be exactly the same as our magnetic quiver at infinite coupling, where I've highlighted in colors essentially the origin, if you want, of the different tails. So far, we have computed the dimension and match, but what's the geometry? Of course, this is extremely hard to compute. However, in collaboration with Subendu, Simone, and Paul, we're putting forward a conjecture whereby the Higgs branch at infinite coupling of the orb instanton should be something, should be a slice in something called double affine Grassmannian of E8. So again, because the LST is a gauging of 2 orb instantons, it's natural to expect that, again, we should apply the hyperkähler quotient to 2 such geometries and obtain the Higgs branch of the LST. However, this poses some difficulties because we know that the slices of the affine double affine Grassmannian are symplectic singularities typically, but on the other hand, we know that we expect this space to be smooth. So, you know, we need to investigate this further. One last point, Michele spent a lot of time speaking about T-dualities. In this talk, I focus only on the E prime LST, so E88 heterotic string, but we also know that we can do essentially play the same game with the spin 32 Fazzi 2 string. So you expect the T-dualities because you expect to be able to construct the magnetic quiver also for the T-dual. In fact, we're doing that. And if you're careful enough, it turns out that the dimension of the Coulomb branch of the magnetic quiver, if you wanted infinite coupling for the spin 32 string, matches with the Coulomb branch dimension of the magnetic quiver for the E88 string modulo, you know, certain shifts, which are precisely consistent with those dictated by the matching of the structure constants of the 2 groups. And on that, I end. Thanks.
Okay, let's thank Marco. And let's have questions to Marco and also Michele.
Let me stop sharing so that if Michele needs to answer.
I mean, you can also share. So I have a question to you, Marco, because you showed the 2 magnetic quivers for if you just have a single O8 minus with the 8s next to it that were done by Ami and Santi and Marcus. And then you were doing this gauging, which basically combined 2 magnetic quivers. But you could just take the brain system you started with and read off the magnetic quiver directly, right?
Yeah, you
there's
can.
There's no difficulty. Okay.
That's exactly.
So you check this is the same thing. Okay.
It's a presentation, if you want, way of doing that.
Okay.
You literally do that and you consider type 1 prime. So here it's obvious, right?
Yeah, exactly. It's obvious.
It's K with the K, and then you transition left to right, break it arbitrarily because you can cut the length, the plateau of the LST at an arbitrary point and declare that the 2 branches are the plateaus. Sure. 2 orb instantons.
And I had a second question about this questionable modification of the Sicilian flag. So I didn't quite understand. Is this now a 4 punctured sphere?
Yeah.
Or is this something else?
Yeah.
So if it's a 4, okay, I see.
Just because of counting the number of punctures, I expect it to be the Sicilian plus. The mirror of the compactification should be the Sicilian plus, if you want.
So
the plus tail comes from the extra puncture.
Like a type sphere with 4 punctures, this would be a quiver with a single node in the middle, right? And then 4 legs coming out. But here you have something more difficult. Like you have
that's your structure, right? That's a node in the middle plus the tails in some sense. Also,
the tails split later. This is what I find I struggle with. But
no, indeed. I mean, I don't want to say that this is exactly what's happening. That's a picture that I have in mind. It may be wrong, just because I have not actually worked out in detail. I was speaking to Yuji as to how to do this, but he's also not completely sure. So how to do this OP of punctures just along a sub part of the puncture. You see what's the
difference?
Because you're gauging a sub part. So that's not been done, at least as far as I know. So maybe.
But then it's not really like a sphere with 4 punctures, right? It's different. So, okay. I agree with the conjectured quiver.
That's why I didn't want to identify the new punctures, with exactly 2 left, 3 left, 2 right, 3 right. These may be some new punctures. I'm not entirely sure. So I do not want to claim things that I cannot prove.
Okay, good, thanks.
So I
Okay,
also have a question.
Sorry, maybe I can comment also. No? In this idea of class S also generalizes to more general G, no? Like in
Sure.
But like what you use is you use class S to construct the Higgs branches for the Orbi instantons, as we know from your works, and then you perform the symplectic quotient, which is a well-defined operation at the level of hyperkähler manifolds. No? And in this way, you can also go to the E-type Higgs branches.
I mean, in fact, there's something called in this paper here, but more into Chicago, there's something called eta functor, eta SUK functor. So in principle, if you invert that, the output of inverting that functor, which associates a TQFT to a class S theory, would be the output of this operation, if this operation here is correct.
Sure. Sure.
Hi, I have a naive question. I just wonder, so I just wonder for all the magnetic quiver or just 3D quiver you mentioned in the talk, so are they all good quivers?
They are, exactly. They're geometrically overbalanced.
Oh, yeah, okay, good.
And they may be balanced.
Okay, can I ask a question about the infinite coupling magnetic quiver that we saw before in the talk? So, yeah, okay. Basically, what we do here is taking two Orbi instanton and gluing them together with some amount of conformal matter in the middle. But if we start directly from the brane picture, we have this floating NS5 brane that I can, like the one associated with conformal matter, that I can choose whether to put them right or left. Yeah. And that's just a choice of where to cut the two quivers. So how would you identify the different possibilities of the cutting in the conformal matter?
So that's a good question. That's why, this is a proposal. You essentially cut arbitrarily, and then you declare any number in the plateau. So the important point is the following. The number in the ramps of compact curves or NS5s, it's dictated upon you. You're stuck. That's it. So at least you're going to have n mu left and n mu right instanton transitions of EA type on the left and on the right. At least you have that. Then how you want to cut the rest is completely upon you. It's irrelevant. So that's just going to add another set of copies, if you want, of E8 affine Dinkins on the left or on the right. At the level of dimensions, of course, this doesn't matter, right? There's absolutely no difference. It may matter if you want to check the structure of the quiver itself against other constructions, such as the class S one, or if you have other ways of constructing them. So the honest answer is, I do not know what's the final prescription. I just know that if you cut arbitrarily along the plateau, you're going to have a consistent answer, essentially, at least at the level of dimensions and visible symmetries on the Coulomb branch.
Okay, thanks.
If that fails against yet another construction, such as the class S1, I don't know. I do not know.
Okay, thanks.
But we know there are different quivers, right? Because you have sort of n choose two different 3D quivers depending on how much you put on the left and the right. And certainly maybe the dimension of the Coulomb branch is the same, but certainly if you were to try and compute something like the Hilbert series, you would see these are definitely different things. So I guess the question is, what is the interpretation?
So I do not know. One proposal would be if you knew where you started from, so you knew that you picked this specific Orbi instanton and that specific Orbi instanton on the left and on the right with this number of curves in the plateau left and right, then you know what to do, right? Because then I glue them at this specific point, but I sort of remembered that I had to smash n left NS5s onto the left wall and respectively for the right one. If you do not know that you start from an Orbi instanton, I do not know the answer. You're right. I have a plethora of choices.
Mm-hmm. But yeah,
maybe that will impact somehow on the geometry of the Higgs branch of the LST somehow. Maybe there's another modding that you need to do because of these multiple choices that you have. I don't know.
Okay. I also had one other question, which was on the very last point
of my talk,
of your talk. Oh, by you, yes, Marco.
Yes.
Yeah, so you didn't talk about T-dualities here. So okay, so there's an immediate sort of challenge in thinking of this last point, which is just take the case where you turn on no holonomy at infinity. On one side, you have a magnetic quiver with an E8 plus E8 flavor symmetry, and on the other side, you have a magnetic quiver with SO32. These are obviously have different Higgs branches, and that makes sense because when you do the T-duality, you have to turn on Wilson lines, and the Wilson lines change the Higgs branch. So how do does the Higgs branch of the 6D LST, as opposed to the Higgs branch of the 5D theory where you turn on Wilson lines, tell you something about T-duality? Or is that sort of a thing which maybe happens if you have no Wilson lines? So I guess the question is,
I understand the question.
Remember that the T-duality is a 5D phenomenon, no?
Right.
It's the equivalence of the 6-dimensional theory on the circle.
Right. So perhaps the 6D Higgs branch is not the relevant object when
you always, if you need to turn on a specific Wilson lines in order to match the global symmetry, then you have to do it. No, in some examples that we have checked explicitly. For instance, the example that I showed in my talk, the symmetry was SO16 times SO16 in both cases, and the T-duality is swapping the number of D6s with the number of NS5s. No? And in that case, we can use that diagram, because the diagram, we know it is faithful because the symmetry is represented consistently, to read off the two distinct Higgs branches and check. No? But indeed, as you point out correctly, you need to look at cases in which you know that the flavor symmetry match. No? In many of the cases that are constructed in F-theory, for instance, it's only a matter of matching of subgroups of the global symmetry, and there, like checking explicitly with this construction of the Higgs branches, I think it's still an interesting open problem, no? Because it requires to turn on a Wilson line on the circle and then like study what is the resulting 5D Higgs branch, and that's not something that we have done in the paper. For the moment, we just check the cases in which we can engineer symmetries which match on the two cases. No?
So where the 6D Higgs branch is the 5D Higgs branch, and then
yes, exactly.
Okay, perfect. Thank you.
Thank you.
Very nice pair of talks, by the way. I enjoyed it a lot.
A question for you, Craig, is to find the F-theory duals of the heterotic strings compactified on C3 modulo gamma.
Sure.
Good luck.
I'll quickly tell you the answer once we turn off the recording.
But yeah, I don't know. I mean, something should be doable just because of the existence of the SL3C Mackay correspondence. So maybe that should help somehow.
But you go on.
Do you have a new perspective on the computations of Hasse diagrams from the stringy picture? The simple thing would be, simplest thing to do would be, construct a magnetic quiver and then follow procedures of subtractions, and you have. But the question is whether the construction itself
gives a new perspective.
Yeah.
It's a good question.
So what I can say is basically what we're doing with Paul. So we did not pass through the subtraction algorithm to construct the, if you want, the Hasse diagram of the affine or double affine guy. So once the definitions are in and you know what you're doing, you can essentially construct the full Hasse just by checking dominant co-weights and subtracting them, right? And we have some mild conjecture on the extension of the result by Malkin, Vibornov, and I don't remember the last name. Ostrich, maybe. So that gives you the type of degenerations, Kraft-Procesi transitions in this specific example, you essentially assume that also holds in the double setup, where you're also changing, in our language, the number of curves in the plateau. And by doing that, you can construct entirely the Hasse diagram. And then
do you find new slices?
No, we do not find new slices. No.
Okay.
So, and once you do that, you can essentially map without passing through the magnetic quiver so a slice, if you want, to a 6D construction. So to a 6D electric quiver. Basically, where do you place the D8s, right? And that's just information contained in the CATS labels. So there is a direct one-to-one correspondence between CATS labels and dominant co-weights. And if you use that, all of a sudden you precisely know, if you just stare at the orb instanton with a certain location structure of the D8s, where you're going to be in the Hasse. So in that sense, yes, if that's a yes to your question, so you can sort of bypass the magnetic quiver, at least in this specific case.
I see. And if you, in the search for simple moduli spaces, let's say you pick a criterion of a linear Hasse diagram or some other criteria, do you have any intuition where can we find such guys?
You mean from 6E or completely in general?
No, yeah, from the experience you had so far. So it's quite a challenge to find simple moduli space.
So I guess
I get excited, but it's a very hard search.
But are you asking whether, given a very simple Hasse, do I know any example or construction as to give you, to tell you what is the physical, let's say, the QFT?
One way of phrasing it, but I'm looking the opposite way, right? I want to get an idea of a large set of simple Higgs bunches which show up in such theories. And the only way I know how to do it is to look at different cases and search for, construct some criteria for simplicity, like
this incident. What's the number that you define in this paper? I think with Julius, incidence. No, what was it? This curly
disposition.
Disposition. Sorry.
Right.
The straight answer is no. I do not know. Maybe using this, correspondence between dominant co-weights in a affine or non-affine Lie algebra, and let me call that, CATS labels in some sense. So embeddings of a finite group into another group. Maybe exploiting that, there is a way to constrain the Hasse that you want to construct, to then tell you what's the group that I need to look at. So the G in which I am embedding, say, ZK, and hence to get something which is simpler in some sense. But you're right. I mean, even in the orb instanton case that we're looking at, the Hasse is super complicated, especially the double one. That's extremely complicated. So,
and then you, because it is like that, you need a very good reason to go and study further such a.
You're completely right. It's just that, physics is pointing us to the fact that new mathematical spaces exist with new Hasse diagrams as their description of their slices. For example, in the LST case, if it is true that this fusion of these two orb instantons has a counterpart at the level of hyperkähler quotient, or if you want holomorphic symplectic quotient, then it's also true that there must be some yet to be discovered, perhaps, mathematical object that has an even more complicated Hasse, which is going into the opposite direction with respect to what you were asking. But still, I think it's interesting.
Let's see.
But for sure, here we're not going to find any simple Hasse diagram.
No.
There's a line. That's just not going to happen.
Definitely.
Another question is
the interplay of this with the complex structure deformation that affects the K trees. No, this is a comment for the. That might be more clear after the seminar next week. but there is a very deep interplay between the flavor symmetries that arise on these little strings and the structure of K3s. These Calabi-Yau's happen to be always fibered by K3s because of the duality between theory and heterotic. And so like the flavor is controlled by a K3. There is always a K3 which controls the flavor. And the two T-dualities will arise, as you will see next week, from choices of polarizations of this K3. And these choices are what says how one flavor lattice is embedded in another. And the Hasse diagram should be something that somehow is related to how patterns of singularity resolutions for these K3s, because they are kind of complex structure deformations for the geometry, which corresponds to the Higgs branch. The only issue is that these are complex structure deformation in a type 2B moduli space where the complex structure is something that you cannot really trust. And so in a sense, the Higgs branch is a deeper tool from this perspective. It really captures the quantum geometry of this compactification. So I would view it as an application of the Higgs branch towards the construction of the quantum moduli space. It's like more, as Marco emphasized in his talk, like this is the moduli space of scalars for the heterotic.
Yeah, but perhaps you want to make some kind of a hierarchy of problems with difficulty. So when you say K3, you have 4 compact directions. Yes. When you construct a T-dual, you have the choice, either 1 compact circle, 2, 3, or 4, right? And the problems will become more and more difficult the more compact directions you introduce.
Yes.
So perhaps now in this case, when you take these 2 sides, it's like you're taking 1 compact direction and you leave the others to be non-compact, right? And you already see this, how the complexity increases quite significantly. Yeah, maybe there should be some program to increase number of compact directions and then to check what kind of consequences you have.
You mean in trying to devising a classification scheme or a organization scheme for this type of information?
Yeah.
Yes.
A la triples, fluxes, and brains, but now on the compact directions of the K3.
To give order to the phase diagrams that arises from the Hasse diagrams, like because the Hasse diagrams can be interpreted as phase diagrams, and now the idea is there an ordering? Is there a principle to decide which are simple, which are not? And it's a very interesting question, Michele. I don't have a good answer.
Okay. Now, how do you treat the cases where you get some coincident Neveu-Schwarz fibrils, right? All of these discrete gauging phenomena. Because Marco mostly mentioned the small
there, no?
Yeah, they are there. It's just that I'd like to hear some comments on that.
But Marco had 2 numbers, which tells you the number of transitions to the left and to the right, and this would include the discrete gauging. In the Hasse diagram, if you do 2 transitions down, then you would see the discrete gauge node.
This
so
is
it's part of it.
What you discussed with Gabi, right? In the paper where you construct all of the phases. Now I collide 2, I collide 3, and so on and so forth, and I will have this mod SN because it's gauged. So good question. I don't know. What I only know is that in the let me call it conformal matter case, with Oren and Diego, we proved, or if you want, we gave evidence from the ADS-CFT perspective that indeed that's gauged. The same thing for the orb instantons has not been done, even though it could be done. So maybe that's one way to approach that.
Yes. So Paul Levy gave us a presentation about the recent work they are going to have, and it is related to these this phenomena where you have coincident n-branes, and it becomes more and more complicated the more n-branes you coincide. So again, here the question is what kind of things could be said beyond that.
So what you're talking about, so for example, symmetric product of C2 is exactly when you have these multi-instanton transitions, and then you take a few sizes to 0, and then you see the symmetric product. And this is a discrete gauging of the free space. So if you have more than one instanton, then you have a combination of the instanton transition and the discrete gauging in some sense. But of course, there is one phase that we didn't see with Marcus, if you would take all the NS5 rings in the middle and clump them together.
That's true,
but,
yes. That I haven't checked.
This is another thing to do.
Yeah.
But I guess if you want to reduce the number of, well, if you want to take the most tensors to, you want to go to the furthest singular point in a tensor branch, then you want to push them either all to the left or to the right or split.
That's just because the question that we're interested in is, you know, what's the multiple modular space? But if you're interested in constructing properties or checking properties of the Hasse, then yes. It also makes sense to consider just the bouquet. You collide all of them together. You have the adjoint, you get the gauge ascent symmetry. Yeah, that's, you know, open.
Yeah, as you move on the tensor branch, you always get a different Higgs branch, and this is but there's no natural origin.
Exactly. Not in this case, at least.
That's the issue that you mentioned. Cool. Do we have any more questions for our duo? Well, okay. If not, I'd say let's thank them both again. This was very nice.
Thanks to you guys.
And we can go off the record.